This is a multi-rotor on the web that you can control. However, this is not just one of those many games on the internet. Instead, this game is dedicated and built for robotics engineers, engineering education, training, and research. In this game, you can use console terminal to spawn a new vehicle or as many as you want. If you want to control, you need to control each of the actuators, as this is designed to understand how the real-world robots would work. So if you were expecting a joystick, you can build one. What the heck I'm talking about, right? Well, simply, you can code this with bare Python or with ROS2, so that you can eventually simulate the multi-vehicle environment with your fancy navigation algorithms. Finally, I'm recording a new video after a couple of months because I have been working on this simulation so I can deploy on the website. For example, you just go to this URL and turn on manual button, then you can fly the drone. That's the basic thing. The different thing is about this control because it doesn't have RC multi-rotor left 2 axes and right side 2 axes, so you can control throttle and then yaw and so on. Instead of doing that, you gotta control every single motor, each single motor like this. Otherwise, it's just going to flip, and then if the controller is not well adjusted, it's not going to fly. And just controlling this throttle is easy, and that's because it's a perfect word. And if you don't like that, you can just go to menu and turn on the noise. And then it's not going to balance by itself, and then it will just crash eventually. But for now, let me just turn off all this noise. Reset this. Actually, the motivation of this game is not to just have fun, but also you need to implement the autopilot algorithm using Python environment like this. This is what I'm going to talk about today. So to get started with, let me just talk about the simulation a little bit more. So if I toggle this menu button, you can have states and settings, and if you go to states, you can literally monitor the current state of your system. Like the position is negatively going up, and that's because the z-axis is downward in this word, so that's why. And then if you want to create a new system, you can just toggle this console terminal, or you can just toggle this menu, or the short key is Control tilde sign. Now you can create a new and tap new multi-rotor like this. Multi-rotor, I don't know, 160 and 2 meters above the ground. And if I go to system 1, which is the new multi-rotor here, or if you just want to load a built-in mission load, then you will have instantly 5 drones as well. If you want to change the view to a little wider view, you can just click view 2. You can see there are like 5 drones, and then if this magic circle is blocking your view, you can turn on this free camera, then use WASD and mouse. Just like a first-person shooting game, you can just fly around with this environment. And then obviously using ROS2, you can control multiple drones like this simultaneously, or using this Python as well. You just need to this VS Code and Python installed on your local machine, and that's it. So for now, let me just turn on this free camera. And then let me clear this, remove all. And then all these robots are gone. And then if you want to create another robot, then just multi-rotor, just create, and then type heli 43,160, and that's just the coordinate that I just memorized, that it can be around this scene. Then there is a helicopter. So that's my helicopter, and then just like multi-rotor, you can increase collective pitch angle of this main rotor, and then it will go up. However, because of the reaction torque from the main rotor, you need to compensate this body torque using tail rotor by increasing the collective angle of the tail propellers. But again, it's quite difficult to do this manually. And if you want to change the attitude, for example, nose down attitude of the helicopter, you can change the cyclic motion like this, then it will nose down. Then what does this mean? It doesn't assume any sort of autopilot. So if you click around this like this angle, and this is the amount of the pitch angle at the back of this main rotor, that's the 0 azimuth angle. And then towards the right side is 90, 180, which is the front of the helicopter, and then 270 degree is just defined as a traditional helicopter azimuth angle definition. And then amount of the pitch angle for this cyclic motion is defined by the distance between center and here. So that's how you want to control the cyclic motion. It's not limited to have a single helicopter. You can have multiple helicopters like this. Helicopter 0, and then I'll create another heli at, I don't know, 30, 160, altitude 2. So that's the helicopter 1. The first helicopter and second helicopter is this. So you can keep creating all these helicopters if you really wish. Now it's bumping with each other because I'm creating the same coordinate, but hey, that's the idea. If you can set up all these positions in a predefined way, which is possible using API, and then you can create your own mission. You can also create all these kind of checkpoints, which is a magic circle. And I'm going to load the default mission. Then I'll go to system 0, and then I'll turn off the camera. Now I'll go up and down. This is the base. Then go up, then it collided with this magic circle and coming back. So if I do list, VR message that list, which is the virtual robot message list, because this simulation is based on publisher subscriber pattern, you can actually subscribe the messages from your virtual robots. So system 0 is there, and then I'm going to subscribe one of the messages called collisions. So I'll type sub, and then I will suggest the possible command vrmsg.sub, and then system ID is 0, and topic is going to be collisions. And then duration is that you can print these messages for like how many seconds, right? But if you don't pass anything, it's just a one-time view to print all these states. So if I subscribe this collision information, it recorded all this history of the checkpoint passing, and at the moment you can see when that happened, and then position of your virtual robot, which is system 0, and the velocity, Euler angles, and all that. So using this, which I mean, you can create your own checkpoints using the API. I'll show you later in the video or maybe next video. But anyway, the idea is that you can create your own arena, say a racing drone arena, and that you want to autonomously control them so that they can pass through a certain checkpoints, and then you want to measure what's the position, what's the velocity. If you want to create your own mission, you can do so. You can also get this information from Python as well, not just terminal. So terminal here is more like a quick debug sort of purpose that you can see what's going on. And for the quick view of the states, you can just use this menu panel. It will be updated in real time. And that's the body force, because the propeller is moving up and down. The most of the simulation like AirSim and robotics, and they are pretty good. And then I'm a big fan of AirSim, by the way. But this only works on the desktop, and then I'm not sure if you can add extra force at your wheel. If you're a researcher, you might want to add additional sort of external disturbance or something like that. Then you can do so by publishing a command like vrmsg-pub add body force torque, or you can use set body force torque. The difference between add and set is that if you use set body force torque, it will override all this body force torque coming out from this system. So your PWM is not going to work. So if you wish to just add external disturbance force, you can add body force torque, and then just type tap. I will just auto-complete. And then you can designate the system ID of your target, and then, I don't know, I'm going to give a weird force like that, and then, I don't know, force for 10 seconds. It's just this force torque is being added on top of these propellers. So if you want to simulate some kind of wind or any random external disturbance, you can do so. Because most of the simulation is quite bounded with their own environment, and I wanted to give a little more freedom to the users. If you wish, you can download the desktop version, which I will release a little later. Then you can interact with these onboard cameras using OpenCVs and so on in real time, so that you can also do some cool SLAM algorithms and so on. So if you like this idea and the simulation, please hit the like button and subscribe my channel. I'll upload more tutorials like this. Now, let me go over the Python part now. So let me refresh this page. And this code is prepared and shared in the Git repo like this. I'll put the link down in the comment section. So just download this Git repo, and then you can read all these readmes. Just install your Python on your local machine, and then install these pip packages. And this is the most important thing, that you can communicate with this simulation. And then there is a module 1. I open up this, and then it's just a simple tutorial. The first thing you want to do is just running this cell. Don't touch anything. It's just a kind of boiler template code. Just run this, and then we'll just run a bridge server so that you can communicate with this simulation environment. It will receive all this information from the web. Then as long as after you see this promising green lines, you can just connect. Then the sample mission here is prepared. It's just maintaining the altitude at 20 meters above the ground. And then 20 meters above the ground, there is a magic circle, first magic circle here. There are like a bunch of magic circles here, and then this yellow one is at 20 meters above the ground, and every other 20 meters, all the way up to 200 meters, there are the magic circles like this. This mission here is to maintain your drone at the center of this first magic circle, and that's the 20 meters above the ground. Before we actually do that, it's just I'm showing you the boiler template code here so that how you can read actual states, subscribe the states from this simulation. Is simply done like this. And then the main function here is this VR client main. It will just connect the simulation automatically, and then we'll just pass this entire class for 10 seconds. It means it's going to run this script for 10 seconds by communicating with this simulation. And then this loop here is just like an Arduino loop. And then this loop function will be called every other, I think is 0.02 seconds, which is about 50 hertz. And then it will just print all these states, that linear position, velocity, system ID, and timestamp. Let's just run this. And then since it's updating the CMD multirotor for this much PWM values, 1500, it is taking off. And then 10 seconds has already passed, it's just finish it, and then when I reset, it doesn't go up anymore. So if I want to change that to, I don't know, 116 for the last motor, which is 0, 1, 2, 3, the last motor will be 16-ish. And if I run this, it's not going to balance, because it doesn't even fly because of torque. Let me see the state. Yeah, the torque is really unbalanced here, so it doesn't really balance in the middle of it. And it has IMU sensors. If I do states, an accelerometer, actuators, and barometer, GPS, velocities, and so on. Do I have gyroscope? Yeah, I have gyroscope here. And then if you really want to practice, say, sensor fusion algorithm, turn on the sensor noise. And then all of a sudden, you are static. All these noises are coming out from the IMU. If I turn off, there's no noise. Or if you don't want to even implement the sensor fusion algorithm, you can just use the ground truth state like Euler. And then now, we are actually implementing the PI controller for the altitude control. And then this is a reusable PI controller for cascade PID controllers. Just run this, then you can type in all these values. How do I know all these KP and KI parameters? Is only because I have tuned before I record this video, and that's why I'm a little bit cheating. But hey, that's it. This is altitude control, and the set point is 20 meters above. And then after this altitude control, I have implemented a velocity controller that you can give a certain PID outputs for all these so that you can maintain these. So let's just run this. Then it will just take off and then slow down, and then it will stop at the center of this yellow sphere. That's the control algorithm I have implemented in Python, and then it's really, I believe it's pretty easy to use. So do you like this simulation? Do you think it's simple enough to get started? If so, please leave a comment down below how you think about this. So that's it for today, and later I'll come up with more tutorials for this.